And thanks, Harold, for an excellent talk as ever. And perhaps we'll ask Rhodri Evans to share his slides. Rhodri, I saw you were online, so. Rhodri, are you there? Rhodri, are you able to share your slides?
Yeah, hopefully you can hear me. Unfortunately, we just had a power cut, which came back on about 3 minutes ago. So, of course, my internet was down. It started about 6 o'clock. But anyway,
right.
I think I'm back on now.
Okay.
Right. Yeah. I missed the introduction, but never mind. I'm ready to start.
No, if you, I didn't give your introduction yet, so.
Oh, yeah, I'm ready. I'm ready. So whenever you want me to go, I'm ready.
Okay. Do you want to share your slides now?
Okay. Yeah.
And then,
okay.
And then as soon as we see the first slide, I'll introduce you properly.
All right. Sounds good. Okay. Share. Okay. I've got to open system settings and give it permissions. Excuse me about this.
Right.
Wonderful. Microsoft Teams. Don't you love it? Okay. I've got to quit and relaunch it because I had to give it extra permission. So excuse me for a minute or two.
Okay.
I don't hear anything. Okay, I'm not hearing anything, but I'm back.
Yeah, I can. Yeah, I can see you.
Right. Let me try and share my screen again. Hopefully, the permissions are all set now.
Okay.
Let me have a look. Screen when. Oh, jeez. Helps when you're not. There we go. I think possibly you can see
coming
something.
Along. There we are. Yeah. If you want to put it on slideshow, then I think we're probably.
Okay, hang on. Just give me a second. I'm not seeing anything, so this is great. I'm not actually seeing my slides, and I can't move this thing. So, okay, hang on. Play slideshow. Okay, let's try this. Did that work?
Yeah, except we're seeing your summaries. We're seeing your next slide as well. So this is like presented.
Right.
We're seeing presented.
Hang on. Let me see if I can switch that. Let me see if I can switch that. Is that better?
That's better. That's okay. Better.
That'll do.
Okay, right. So I think we're all set. Good evening, everybody. It's great to see everybody, and particularly Rhodri, who's giving at least his second talk, I think, to the Society, so he's familiar to many of you. But Rhodri is a senior lecturer at Buist, joining in 2022 from University of Namibia. Did his PhD at the University of Cardiff in Wales, here in the UK. After doing a BSc at Imperial College in London. He's worked at University of Cardiff and University of Chicago on research projects on instrumentation in far infrared, millimeter, submillimeter part of the spectrum, I think. And also was assistant professor at the University of Toledo in the US. As well as his research work and his teaching, he is a great advocate for the promotion of public understanding of science, and he's written 8 books popularizing astronomy. And at Buist, he's building a research team focusing on furthering our understanding of the cosmic microwave background, particularly centered around access to the Simons array. And it's that aspect of Rhodri's work that we'll hear more about tonight under the title of Searching for Evidence of Cosmic Inflation. So, Rhodri, the floor is yours.
Thank you very much, Mike. Hopefully you can all hear me okay. So yes, as Mike said, the title of my talk is Searching for the Evidence of Cosmic Inflation. I'll obviously explain what cosmic inflation is if you don't already know. So the summary of my talk, if you want to take a 40-minute nap, is first of all, I'll talk about the expansion of the universe, which I'm sure a lot of you already know sort of exists, as it were. The universe is expanding. It turns out that there were 2 competing theories for the universe, the so-called hot Big Bang and the steady state. So I'll talk a little bit about them, and then I'll explain the accidental discovery of the cosmic microwave background by Penzias and Wilson, and explain where cleaning out the pigeon droppings comes into the story. Boys, we've been scooped is the realization by another team that Penzias and Wilson had discovered the cosmic microwave background. Then I'm going to sort of jump 30 years really to the early 90s, when the era of what we now call precision cosmology started. And this was really with the advent of satellites that could do this kind of work from space. And then I'm going to finish up by explaining what cosmic inflation is, how we can actually detect it with something called the B-mode polarization, and then Buist's involvement in the Simons array. So some of this talk is based on a book that I wrote. Mike mentioned I've written 8 books. This was actually the first one that I wrote. The cosmic microwave background and the story of its discovery had fascinated me for a couple of decades, really. So I got an offer to write this book through Springer and had a lot of fun writing it. Although I thought I knew the story of the cosmic microwave background's discovery, I learned a lot more writing the book. And so if you want a copy of this book, I'm not even going to charge you. I will just send it to you through email, PDF file. So my email address is on the first slide, but it's also obviously in the email that goes out to the whole society. I just wanted to mention about how science advances. So if I were given this talk 60 years ago, most physicists would actually have said that the idea of the Big Bang was wrong. And yet just a few years later, the Big Bang had gained wide-scale acceptance, and that's essentially because of the discovery of the cosmic microwave background in 1965. So I found this quote, about 7-8 years ago now, which I like, which says, "Science never gives up searching for the truth, since it never claims to have achieved it. We are, of course, always looking for the flaws in our current understanding so that we can understand more." Right, so the expanding universe. The first person to derive solutions to Einstein's equations for an expanding universe with matter in it was a brilliant Russian mathematician by the name of Alexander Friedmann. And in 1922, he published the first theory, as I just said, of an expanding universe with matter in it. Sadly, he died just a few years later in 1925 of typhoid. And then independently in 1927, a Belgian priest by the name of Georges Lemaitre came up with the same idea. Obviously, back in those days, it was much easier to not know what other people were doing. So he essentially published the same idea. And he even predicted the expansion rate of the universe. Excuse me, just got to close the door. Which not a lot of people know. So in 1927, Georges Lemaitre predicted that the universe was not only expanding, but he actually predicted the expansion rate of it. And unfortunately, no one took any notice of this work. He published it in an obscure Belgian journal, which wasn't widely read. So although it was important work, it just didn't get noticed. But then in 1931, it was translated into English by Sir Arthur Eddington, who possibly wasn't a sir at the time. And when it was translated into English, even Einstein took notice. Meanwhile, on the observational side, Edwin Hubble, by the end of the 1920s, had gathered enough evidence to show that the universe is expanding. Basically, he looked at galaxies, could measure their recession velocity using the redshift, worked out their distance using various methods, and found that there was a very simple relationship between the distance of a galaxy and how quickly it was moving away. And the most natural, simplest explanation of this is that the universe is uniformly expanding. So a few years later, a couple of years later, in 1931, Georges Lemaitre proposed that the universe had begun as a primordial atom. So Georges Lemaitre is sometimes referred to as the father of the Big Bang because he was the first person to suggest that the universe began in a sort of finite moment of creation. I've highlighted the bit of his letter to Nature which mentioned this, but here's an expansion of it. So remember, this is the early days of quantum mechanics. So he said, if the future development of quantum theory happens to turn in that direction, we could conceive the beginning of the universe in the form of a unique atom. So this was essentially the first ever mention in the scientific literature, at least, of a creation event, the so-called, what we now call the Big Bang. But it turned out that after the Second World War, so we jump forward maybe 14 years or so to 1945, 46, George Gamow, who was a Russian who had emigrated to the United States, and Fred Hoyle, who was a British astronomer, they had competing cosmology theories. So let me first of all talk about Fred Hoyle's steady state theory. So English astrophysicist Sir Fred Hoyle, he just, from a philosophical point of view, did not like the idea of a beginning to the universe. He philosophically wanted to argue, and did argue, that the universe had always existed. So he proposed that the universe had always existed, and although he didn't argue that it was expanding, he argued that new matter was being created all the time to keep the density of the universe the same. And this became known as the perfect cosmological principle. So the cosmological principle states that the universe is the same in every direction, and it doesn't matter where you go in the universe, it'll look the same. Or what Fred Hoyle was adding to that was that it would actually look the same whenever you looked at it. So it didn't matter whether you looked at it now, or 10 billion years ago, or 1,000 billion years ago, it would always look the same. So this became known as the perfect cosmological principle. And in a radio interview in the early 1950s, he coined the term Big Bang as a disparaging term for the other theory that he didn't agree with. Then in the other corner was Russian-American George Gamow, and he built on Lemaitre's idea of the primordial atom that I just mentioned. And actually, he'd been a student of Alexander Friedman, and then he emigrated to the United States. And he proposed that all of the elements had been created in the early universe. And this is referred to as any elements that are created in the early universe. We call it primordial nucleosynthesis. So Gamow believed that all of the elements had been created in the early universe. And he had a PhD student by the name of Ralph Alpher working on this. And in 1948, when Ralph Alpher had finished his PhD, they published what has become an infamous paper, the famous Alpha Beta Gamow paper. Here it is. So Ralph Alpher and Gamow were working together. And then Hans Bethe was a world-renowned nuclear physicist at Cornell who knew nothing about this paper, but it was Gamow's joke to have an author list that read Alpha, Beta, Gamma. So beta was added in order to be able to sound like the Greek letter beta. But it is a very famous paper, not just because of the joke in the author list, but because it tried to work out a physics where all of the chemical elements were created in the early universe. And then in the same year, October of 1948, in Nature, and I mention this because before I started doing my research for my book, I thought that this work by Gamow and his colleagues in the late 1940s had been published in obscure scientific journals, but that's not the case at all. They were publishing in Nature, which is the most prestigious scientific journal. So in October of 1948, publishing in Nature, Gamow published an article, a paper called The Evolution of the Universe. And in this paper, he calculated some of the consequences of his idea that all of the chemical elements were created in the early universe. And then his, by now, 2 postdoctoral assistants, because Ralph Alpher had finished his PhD, and his other postdoctoral assistant by the name of Robert Herman, they found a mistake in their boss's October paper, so they published a correction which appeared in December 1948. And before I move on, it was rumored that George Gamow was trying to get Robert Herman to change his name to Delta so that he would have alpha, beta, gamma, delta, but that's probably not true. Anyway, at the end of this paper that Alpher and Herman published in December 48 in Nature, they made a mention of a relic radiation at a temperature of about 5 Kelvin, which for those of you who know about science, it's 5 Celsius above absolute zero, a temperature of minus 268 Celsius. And this is the paper, the entire paper, very, very short, as you can see, more of a letter, I suppose, than a paper. But in the bit that I've highlighted, they mention that there should be this relic radiation left over from a hot, dense early universe, and that would have had a temperature at the time of its creation of 600 Kelvin, but because of the expansion of the universe since then, it would currently have a temperature of about 5 Kelvin. So this is the first ever prediction of the cosmic microwave background in December 1948. So what causes the cosmic microwave background? So when the universe was young, it was smaller and hotter, and the hydrogen, which makes up pretty much all of the universe apart from helium. So essentially 74% of the universe is hydrogen, some 25% is helium, and everything else is about 1%. So in the hot early universe, you had hydrogen and helium, and it was all ionized. And when you have an ionized gas, photons cannot travel freely because of scattering of free electrons, so-called Thomson scattering. So the photons were essentially trapped, so the gas was opaque to radiation. But the universe is expanding and cooling all the time. And when the universe had cooled to a temperature of about 3000 Kelvin, this is cool enough for neutral hydrogen atoms to form. So this is referred to by astronomers as recombination. And I've always disliked this term because it was combination for the first time of the protons and the electrons to form neutral atoms. So I much prefer the term decoupling, which essentially is saying that matter and radiation decoupled. And at this moment, or at this time, it wasn't a single moment in time, but over a period of maybe a few thousands of years or hundreds of years, the universe had cooled enough to become essentially transparent, and the photons could travel freely. So you go from a situation where the photons were trapped to being able to travel freely, and this is the light that we see in the cosmic microwave background. And this happened when the universe was about 350,000 years old. So the universe we know is 13.7, 13.8 billion years old. So this is when the universe was just 0.003% of its current age, very, very early in the life of the universe in most ways of measuring it. So after making this prediction in the December 1948 paper, Gamow, Alpher and Herman tried to persuade the radio astronomy community to look for this relic radiation because they knew it would be at wavelengths which coincide with radio wavelengths. Something at 5 Kelvin is not going to emit visible light or even infrared light. It's going to be found in the radio part of the spectrum, or really microwave. And they took their theoretical prediction to different radio observatories in the early 1950s. And for a period of over 10 years, they tried, but every radio observatory told them that it was too difficult and would never be found, that if the signal existed at all, it would be so weak that it would never be found. So eventually they gave up and moved on to other work. And as an interesting personal connection, I had a job interview at a college called Union College in Schenectady, New York State. And Ralph Alpha was on the staff, and I got to meet him. And this was 1995. Now, unfortunately, I didn't know as much about this CMB stuff back then as I do now. So although I knew of him and knew that he had been involved in some way in CMB work, I just wish I'd met him some 20 or 30 years later when I could have quizzed him much more thoroughly. So now we're going to jump to the accidental discovery, which happened essentially in 1964-65. So in 1964, Arno Penzias and Robert Wilson were working for the Bell Telephone Labs using this strange-looking antenna on the right here, known as the Holmdel antenna in a place called Holmdel, the state of New Jersey. And they had access to this antenna, which was at the time the most sensitive radio telescope in the world. And it had been built by Bell Telephone Labs, who were, of course, a communication company, as part of the Telstar satellite program. So the United States was planning to launch communication satellites for the first time. And as part of testing the essentially some of the stuff that they would need to be able to do for communication satellites, they built this antenna. And then what they were doing was sending a helium balloon up high into the atmosphere and bouncing radio signals off it and seeing whether they could detect those radio signals being bounced off this helium balloon by this very sensitive antenna. So that was, the telecommunications work that they were doing with this antenna. But Penzias and Wilson were radio astronomers. They both got PhDs in radio astronomy. So what they wanted to do with this incredibly sensitive antenna was look for tenuous neutral hydrogen gas on the outskirts of the Milky Way galaxy, which at this point had never been detected. So of course they knew they were going to be looking for a very, very faint signal, but they had the most sensitive radio antenna in the world, so why not try? So because they knew the neutral hydrogen they were looking for would give off a very weak signal, they needed to thoroughly characterize the instrument. And what I mean by that is they needed to account for every element of any signal that they were detecting. So for example, the sun gives off radio waves, the Milky Way gives off radio waves, of course, radio transmissions give off radio waves almost by definition. Even cars, when you've got the engine running, give off radio waves, and electrical wires give off radio waves, particularly if they're not well insulated. So they had to eliminate all of these signals in order to try and find the very, very weak signal that they were anticipating might be coming from neutral hydrogen. But even after they'd eliminated all of these other known sources of radio emission, they found a persistent hiss, a persistent signal that they just did not seem to be able to get rid of. It was their night and day, so it couldn't be the sun. It was their winter and summer, so it couldn't be the center of the Milky Way galaxy. And it was the same in every direction in the sky. So at one point, they thought that it might be pigeon droppings, because it turned out there were some pigeons nesting in the nice cozy horn of the antenna. So they cleaned out all the pigeon droppings, took the pigeons some 75 kilometers away and released them. Unfortunately, the pigeons were homing pigeons, so they were back in the antenna within a few days. So this time they cleaned them out again and they didn't release the pigeons. But even after they cleaned out all the pigeon droppings, the signal was still there. So at this point, they were totally confused and could possibly have just given up and thought, well, we don't know what the signal is, but we'll just accept that it's there and we'll continue trying to look for the neutral hydrogen, which is the project they were trying to do. But then, as luck would have it, in January of '65, Penzias was going to a meeting in Canada, and he happened to sit next to a radio astronomer by the name of Bob Burke on the aeroplane. Not, I suppose, not that surprising if you go into a meeting, but you might share a seat with someone else going to the same meeting. And Burke had just attended a talk that Bob Dickey had given. So Burke said to Penzias, you should contact Bob Dickey at Princeton because he's working on a theory of a relic radiation left over from a hot early universe. And this is a theory that Dickey and his student Jim Peebles were working out the details of. As you can see, essentially the same idea as Gamow and his postdocs had come up with in the late 1940s. And in fact, Dickey had an experimental team, Dave Wilkinson and Peter Roll, who were building an experiment to detect it. And as I learned more about Bob Dickey, I became more and more in awe of the man. He was probably one of the very few 20th century physicists who was both a world-class theoretician and a world-class instrumentalist. And he, for example, developed an alternative theory of gravity known as the Brans-Dickey theory. And during the Second World War, he built a very sensitive radiometer, which is still known as the Dickey radiometer. So a world-class instrumentalist and a world-class theoretician, which is extremely rare, particularly by the time you get to the 20th century. So Penzias had been advised by Bob Burke to call Dickey, so he did so one lunchtime. And Dickey's habit was to have his postgraduate students in the office with him. So the postgraduate students were sitting around whilst Dickey took this phone call, and you can actually read an account of Dave Wilkinson's memory of this lunchtime phone call, where he could hear Dickey sort of saying yes, no, and answering various questions. And then Dickey came off the phone and said to his team, boys, we've been scooped, because he knew that Penzias and Wilson had discovered this relic radiation. So the two teams decided to publish their results together in the July 1965 volume of the Astrophysical Journal. So the Penzias and Wilson team, who had actually made the discovery, of course, they were going to announce this discovery with a title that would grab your attention, such as Discovery of the Relic Radiation from the Hot Big Bang. But obviously the Bell Telephone Laboratories were not, their PR team were not working that day, because the title to the paper is a measurement of excess antenna temperature at 4,080 megacycles per second. Hardly a title that's going to grab your attention. So probably very, very few people read it. It's a highly technical paper, just talking about all the details of their experimental work. And the only mention they make of the significance of their discovery is right towards the end, where they say a possible explanation for the observed excess noise temperature is the one given by Dickey, Peebles, Roll, and Wilkinson in 1965 in a companion letter in this issue. And below you can see the abstract of the companion letter, which is where the Princeton team laid out the significance of this excess antenna noise. Now, amazingly, Dickey was completely unaware of Gamow's team's work from 1948. And when I knew he was unaware, I just thought, well, Gamow must have been publishing in obscure journals, but he was publishing in Nature. So it is quite amazing that Dickey was unaware of it, but he genuinely was. And after Gamow got in touch with him and said, oh, we predicted this 17 years ago, Dickey always credited Gamow and his team with having made the first prediction of this relic radiation. So this discovery was made in 1965, and now let's jump forward to the end of the 1980s with the launch of a very important satellite called COBE, Cosmic Background Explorer. It was launched in 1989, and in 1990, after about a year of observations, it was able to show that the cosmic microwave background is a perfect black body, which was an important part of the theory as to what was causing it. This is the spectrum that they obtained with an instrument called FIRAS, the Far Infrared Spectrometer. And one thing I want to point out to you, the temperature of the black body is 2.725 Kelvin. It is the most perfect black body ever measured in nature, and the error bars are 400 sigma, so roughly 100 times larger than we normally show error bars. And that's just because if we showed them the normal size, you wouldn't see any error bars, and people would think that you'd forgotten to put them in. So this is, as I say, the most perfect black body ever measured in nature, and really gave resounding confirmation to the theory as to where the CMB had come from. And then after about 3 years of observations, Kobe had built up enough data to discover what we call anisotropy. So remember, isotropic means the same in every direction. So anisotropic means not the same in every direction. So these anisotropies had been predicted by theoreticians for a couple of decades, but no one had ever seen them, and Kobe was able to see them after some 3 years of observations. So this, when it was announced in 1992, was considered one of the most important discoveries in science of the 20th century, because what you're seeing in this image is the beginnings of the structure of the universe that we see today, the beginnings of the clusters of galaxies and the voids, the filaments and the voids that we see. Then about 10 years later, a better satellite was launched called WMAP. So it was initially called MAP, which stood for Microwave Anisotropy Probe, but in the preparation, working on the satellite, which usually takes 10-15 years, Dave Wilkinson died. So the W is for Wilkinson, so it was named partly in his honor. The W is named after him. So this was launched in 2001. And this is the map of the anisotropies that it produced. So you can see it's a lot clearer, a lot sharper than the one that Kobe produced. And so just to kind of show the evolution from the first detection in 1965, where you've just got essentially a single temperature for the microwave background. Then by 1992, we could see tiny temperature fluctuations in the cosmic microwave background, but not with very good resolution. And then by 2003, with the work of WMAP, we could see those temperature fluctuations with much, much more detail. And then just to come to the best map that we have of the whole sky. So Planck, which was a European satellite named after Max Planck, was launched in 2009. And this is the map that it produced. So Kobe, WMAP, and Planck, you can see the resolution, the detail is just getting better and better as we come closer to the current day, just because of better technology, more detectors, and all the rest of it. So it turns out that by studying the anisotropies in the CMB, we're able to determine important parameters about the universe. So over on the right here, we have what is referred to as a power spectrum. On the y-axis, we have essentially the temperature variations from the average temperature. And on the x-axis, we have angular scale going from larger to smaller angular scale, and it's logarithmic as we go from left to right. And all of the black data points that don't seem to have any error bars are from WMAP. And then as you go to higher angular scales, these are ground-based observations, which have much, much larger error bars because you're trying to do it through an atmosphere which is absorbing a lot of the radiation that you're trying to observe. But theoretical models to fit these data give us, for example, that the age of the universe is 13.7 billion years old, that the expansion rate is 72 kilometers per second per megaparsec, the Hubble constant. It tells us that the geometry of the universe is flat. It even gives us the percentage of normal baryonic matter as being just under 5%, the percentage of dark matter at about, let's say, 25%, rounded up, and the percentage of dark energy as being just over 70%. So our current model of the composition of the universe is a very weird composition, where only some 5% of the universe is made up of normal matter, 25% is made up of dark matter. We don't know what that is, and some 70% is made up of dark energy, and we don't know what that is either. Now let me move on to cosmic inflation. So cosmic inflation was first proposed by particle physicist Alan Guth, whom you can see in the picture here, in 1980. And he came up with the idea to address a problem in particle physics, which is known as the magnetic monopole problem. But conveniently, as you will see, it's a very simple idea, but conveniently, it actually solves two other problems in cosmology, namely the horizon problem and the flatness problem. So let me explain each of these three problems in a little bit more detail. First of all, the horizon problem. So Partridge and Wilkinson from the team that Tiki put together, and then Partridge joined them, and they found in 1967 that the CMB varied by less than 0.1% of its approximately 3 Kelvin temperature anywhere in the sky. Now, the universe, the CMB, as I've already mentioned, was produced when the universe was about 350,000 years old. But if you work out the size of the universe at this time, there was not enough time for photons in different parts of the sky to communicate with each other. So how on earth would one part of the sky know what the temperature of the other part of the sky was? They shouldn't be at the same temperature because they hadn't had time to communicate with each other. The photons would just take too much time. So this is known as the horizon problem. The horizon is too big for photons to communicate in different parts of the sky. Then the flatness problem, as many of you know, in Einstein's theory of gravity, the curvature of space is actually related to the strength of gravity and also to the future of the universe. And we define something called the critical density, and that's the density that the universe needs to have to be flat, to have a flat geometry. So a flat geometry means that the universe will expand forever, but it will take an infinite amount of time to do so. So an open universe would expand more quickly. A closed universe would expand, eventually stop and contract, and a flat universe is the borderline between the two. So it will expand to infinity, but it will take an infinite amount of time to do so. And as Woody Allen said, eternity is a very long time, especially towards the end. So omega, capital omega, is the ratio of the overall density to the critical density. This is the way that physicists quote these things. And omega subscript m is the ratio, for example, of matter to the critical density. So it turns out that if the critical density is within a factor of 4 to be in unity now, and unity means a flat universe. So if the critical density is within a factor of 4 of being 1, so in other words, if it's as low as, let's say, 0.25 or as high as 4, it would need to be within a factor of 10 to the minus 60 of unity in the very early universe. And of course, that seems like it would be incredibly unlikely. So why does the universe appear to be flat when it would need to be within unity, but to a factor of 10 to the minus 60 when the universe was very small? And then finally, the magnetic monopole problem. So as I say, this is more of an issue for particle physicists, and it's what motivated Alan Guth to come up with the idea of cosmic inflation in the first place. And as a lot of you know, in electricity, obviously we have positive and negative charges, and James Clerk Maxwell's laws of electromagnetism predict that there should be isolated magnetic monopoles, or to put it another way, that there should be isolated north and south magnetic poles. So you should have naked north and south poles, but we have never seen a magnetic monopole. All magnets have both poles, and we've never actually found a magnetic monopole. So how does cosmic inflation, well, first of all, let me describe what cosmic inflation is, and then I'll explain how it is able to solve each of these three problems. So cosmic inflation is the idea that when the universe was about 10 to the minus 36 of a second old, until it was about 10 to the minus 32 of a second old, it underwent a period of very, very rapid expansion or inflation. So at the start of cosmic inflation, the universe was smaller than an atomic proton, but by the end of this brief period, it was about the size of a marble, which is an increase in size of about 10 to the 13, even though the increase in time is 10 to the 4. So if you divide 10 to the minus 32 by 10 to the minus 36, you of course get 10,000, so that was the increase in time, a factor of 10,000, but the increase in size of the universe was about a factor of 10 to the 13. After this very, very brief period, the universe settled down to sort of normal expansion. And remarkably, this very simple idea solves all of the three problems that I just mentioned. So let me explain how it solves them. The horizon problem is solved simply by allowing the universe to be a lot smaller before inflation and then undergoing this very rapid expansion, meaning that parts which were thought to be too far apart to have ever communicated would have actually been close enough before inflation to communicate and share their temperatures with each other. The flatness problem is solved by arguing that we're only actually seeing a tiny part of the universe, the so-called observable universe, and the actual universe is much, much bigger. And if you look at the geometry of any surface at a small enough scale, it's always going to appear to be flat if you make the scale that you're looking at it small enough. And the magnetic monopole problem is solved by arguing that they were created in large quantities before this period of cosmic inflation, but because we only see a tiny part of the universe, all of the magnetic monopoles are in a part of the universe that we are not able to observe. Okay, so how are we going to detect cosmic inflation? Well, polarization patterns in the cosmic microwave background separate geometrical into what we call E and B modes. The B modes possess a handedness, and I'll explain that in a diagram in a second, and they are produced by gravitational waves. Density fluctuations in the universe do not produce B modes, gravitational waves do. So when we look at a polarization pattern, there are two directions that we can pick out in a polarization pattern. One direction is the direction picked out by the orientation of the signal, and the other direction is that picked out by the signal's amplitude. So as an example of that, here we've got a plane wave coming towards us. And so the wave is going up and down. Imagine this wave coming towards us going up and down. And I've drawn on this diagram, well, I got it off the internet, actually, I didn't draw them. You can see in orange, we've got E, and in purple, we've got B. So if the polarization is parallel or perpendicular to the direction of motion of the waves, then we have E mode polarization. And if the polarization is crossed at 45 degrees to those angles, we have B mode. So here I have an example of E mode polarization in, this isn't actually the cosmic microwave background, it's a sort of a synthetic signal. And then here we have the B mode, and you can see that they look different. Another way of thinking about this, which may be a little bit easier, is in this following slide. So the CMB is actually polarized at a level of a few millionths of a Kelvin. Remember, the temperature of the microwave background is 2.7, and then superimposed on that at a level of a few millionths of a Kelvin is the polarization. As I've already said, there are two types of polarization, and we name them by analogy with electrostatics. So the E mode is curl free, and what that essentially means is that you can fold it and it'll be able to fold on top of itself. It has a symmetry, or at least a symmetry that is kept if you fold it. Whereas, before I move on to B mode, the E mode polarization of the CMB was first detected by an experiment called DAISY, which was at the South Pole, and this was detected in 2002. And this was a team from the University of Chicago who were working on this experiment when I was there, but I'd just left before they actually made the discovery. And then the B mode polarization, which you can see on the right, looks different. So this has curl. And so if you try folding this, it won't lie on top of itself in the same way that the E mode does. And the B mode polarization is predicted as being due to two processes in the universe. One is cosmic inflation, and the second is large-scale structure in the universe, essentially gravitational lensing, because remember, B mode is produced by gravitational waves. So if you have gravitational lensing, you'll have gravitational waves. So in 2014, there was much excitement because BICEP 2, an experiment at the South Pole, announced that they had discovered cosmic inflation. And here is their result. So don't worry about all the stuff down towards the bottom of the plot. That's all the sort of background signals. But the dashed line with the data points is the signal that they detected. And you can see quite clearly that there is a definite detection of what they interpreted as being B-mode polarization in the cosmic microwave background. This is the experiment at the South Pole. So it turns out the South Pole is an excellent place for doing this kind of work because it's very cold. So there's very low water vapor in the atmosphere. So you can detect these signals at microwave wavelengths on the ground, as it were, on the plateau in Antarctica. But then within weeks of this announcement, other explanations for the detected signal were proposed. And here is an image showing the patch of sky that BICEP 2 was observing in the bottom picture here. And in the top picture is the emission from our Milky Way galaxy that the Planck satellite had detected from dust in our galaxy. But notice that they had blanked off the part of the sky where BICEP 2 was looking, because Planck had the answer as to what BICEP 2 had detected. So about a year after their initial announcement, they withdrew their claim because the detected signal was actually due to dust in our Milky Way galaxy and not, unfortunately, cosmic inflation. A lot of people criticized the BICEP 2 team for announcing their results too early. But in my opinion, it gave a nice illustration of how science works. They announced their results, maybe a little bit early, who knows, but then the scientific community set about questioning whether their results were correct, and the Planck team were able to release evidence showing that they were wrong. So, of course, science is based on observations and fitting observations to theory. So they wrote a joint paper, the BICEP 2 and Planck team, essentially withdrawing the claim that they had, the BICEP 2 team withdrawing the claim that they had discovered cosmic inflation. So now let's move on to the precursor to the Simons array. This is a telescope called Polar Bear 1, and it operated from the Charging-Anchor Plateau of the Atacama Desert in Chile, which is at an altitude of 5,200 meters and is actually the driest place on Earth. And Polar Bear 1 was led by Professor Adrian Lee of University of California, Berkeley. It began observations in 2012, and in 2019, it was decommissioned. And the nomenclature we give for the angular power spectrum of the primordial B modes is C subscript L. The L is the essentially the angular resolution, and the two B's at the top is telling us that we're looking at the cross correlation of the B mode polarization. And the receiver on this telescope, the thing that does the detecting, contained more than 1,200 polarization sensitive detectors, and they were able to detect a signal from a B mode signal from the CMB, but it wasn't, at least they weren't able to show that it was due to cosmic inflation. It was probably due to gravitational lensing, but back in 2014, they showed that at least the concept was working and that the telescope was sensitive enough to do these things. So this is their detection, which doesn't look very spectacular, but in fact, it's pretty important that the data points for at least 3 of them are non-zero, even including the error bars. I'm just going to talk a little bit about the Charging-Anchor Plateau before I come back and talk about the Simons array. So ALMA, which stands for the Atacama Large Millimeter Array, is on the Charging-Anchor Plateau. And this went into operation in 2013. And it has 66, or at least I should say it started operations in 2013. It has 66 radio dishes as of now. 25 are 12-meter radio dishes, which were provided by North America, the North American contribution to the project. A further 25 12-meter dishes were provided by the European countries involved in the project. And then there are 4 12-meter Charging-Anchor Plateau it's in northern Chile, and as I say, it is at an altitude of 5,200 meters. It's the driest place on Earth, so it is ideal for doing this kind of astronomy. And the Simons array has essentially followed on from Polar Bear 1. So the Simons array consists of 3 telescopes. The Nicholas Simons telescope, that's named after one of the sons of Jim Simons, who put up a lot of the money for this. The second telescope is the Paul Simons telescope. And the third one is the Juan Tran telescope. And this is Polar Bear 1, which has been renamed. Now, I had no idea who Juan Tran was, but I looked him up. And he was a research physicist who sadly died in 2009 while sleeping at the young age of 35, born in Vietnam, and moved to the United States when he was 7 months old. And he worked at University of California, Berkeley. So the third telescope is named in his honor. And the Simons array is funded by the Simons Foundation. Jim Simons is a multi-billionaire who made his money on hedge fund management. The Moore Foundation, one of the co-founders of Intel, and finally the National Science Foundation, which is one of the government agencies that funds science in the United States. And on one of the telescopes, there are 22,764 detectors, which is 18 times the number that were on Polar Bear 1. And they are cooled to a temperature of just 0.25 of a Kelvin, 250 millikelvin, which takes a lot of effort, but it's worth it. And they make observations at 90, 150, 220, and 270 gigahertz, which for anyone who knows about radio astronomy is very high frequency. And they are you can control them fully remotely. So in fact, BIOST is becoming involved not only in this project, but also in helping out with the remote observing, because it essentially is a 24-hour cycle to get the instrument ready for making observations and then to make the observations. So there are going to be 3 teams, one in Japan, one in our time zone in Botswana, and then the 3rd team in California, who between the 3 of them can help prepare and operate the instrument around the clock. Here are some pictures of the instrument. I'm not going to say too much about this, apart from the fact that these things are pretty large. So this instrument is probably about 2 meters long and maybe 50 centimeters or so in diameter. And the important thing is there's a lot of technology in these instruments. This is the kind of thing that I love and have built in the past. In the PB2A receiver. So these pictures are of PB2A, and in PB2A, PB being polar bear. So polar bear 2A, there is a warm half wave plate. So it's the half wave plate that allows you to measure the polarization. And in PB2A, it's warm, basically it's not cooled. But in PB2B, it's actually cooled down to low temperatures, cryogenic, which reduces the noise in the system. So it's advantageous to do that, even though it's a lot of work to cool something that large down to very, very low temperatures. So what's the current status of the Simons arrays? So PB2A and PB2B both have detectors on them. So the 2 telescopes both have detectors on the back end. That wasn't the case a year ago. And the project is currently funded until October of 2024, which is actually not that far away in the future now, but they are looking for continued funding. And the total cost of the project to date, from when the Polar Bear 1 was decommissioned and Simons array was started, is about 15 million US dollars. BIOST currently has 2 MSc students working on this project under my supervision, and I'm currently looking for funding within Botswana and possibly outside of Botswana to add maybe 3 or 4 more MSc students and hopefully 2 PhD students to this project, so we can have quite a decent sized team at BIOST working on it. Now, the successor to the Simons array is known as the Simons Observatory. So if you Google Simons array, unfortunately, you won't find a page about the Simons array. You'll find a page about the Simons Observatory, because this is the future. And this should be under construction in the next 1 to 2 years. It will have a total budget of over 150 million US dollars, so essentially a factor of 10 larger than the Simons array. The Simons Observatory will consist of 1 6-meter large aperture telescope. I should say the 3 telescopes in the Simons array are all the same size, and they're 2.5 meter, but the Simons array will have 1 6-meter large aperture telescope and then 3 smaller aperture telescopes, all of the same size, so 3 small aperture telescopes. And there will be approximately 60,000 detectors on the 4 telescopes, about half of them on the large aperture telescope and the remainder on the small aperture telescope. So you can see how the number of detectors has increased as the years have gone on. And of course, it's a huge undertaking to build this many detectors. So BEOST is in very preliminary discussions to join the Simons Observatory project. First of all, we need to officially join the Simons Array project, which I was hoping would have happened by now, but there's been a few delays, but it's still, we are still on course to officially join it. And then hopefully we can use that as a way into the much more ambitious Simons Observatory project. So just to conclude, there's now overwhelming evidence that the universe began in a hot Big Bang. And since the discovery of the cosmic microwave background anisotropies in 1992, detailed observations of the power spectrum has led to the dawn of what we call precision cosmology. One of the biggest questions in cosmology is whether cosmic inflation actually took place. It leaves a fingerprint in the form of B-mode polarization on the CMB. So several experiments in Chile, one at the South Pole, and some experiments in the future in space will be looking for this elusive, very faint signal of evidence of cosmic inflation. And the Simons Array is currently the biggest experiment making observations to detect this B-mode polarization, soon to be superseded by the Simons Observatory in the next 3-4 years. And BEOST is part of this world-leading project, I'm pleased to say. So I will end my presentation there and obviously be happy to answer any questions.
Well, thanks ever so much, Rhodri, for a fascinating, very wide-ranging talk. I really love the sort of history of things here, and a lot of nuances that I really didn't know about, and that was fantastic. Thank you very much.
Okay.
So yeah, questions. There's one in the chat from Stuart Morongway.
Right, let me have a look. Oh,
it's quite
LICEP array is experiment. Oh, yeah. Okay, so I'm going to jump to the end of the question. What would be the impact of such a discovery on cosmology and astrophysics? Are you also working on inflationary cosmology? So no one has yet detected definitive evidence for this B-mode polarization from cosmic inflation. So either it's there or it's not. And if we do detect it, it would be stunning confirmation that this idea of the rapid expansion when the universe was between 10 to the minus 36 and 10 to the minus 32 of a second old is correct. If we don't detect it, it's either that the signal is weaker than predicted and it is there, or it isn't there. And if it's not there, we have to revise our ideas because it would suggest that cosmic inflation is incorrect. Am I also working on inflationary cosmology? So I'm not sure if you mean cosmic inflation by that, or if you're talking about the accelerating expansion of the universe, which is what dark energy seems to do. I'm not working on dark energy. I'll leave that for people with far more ability than I've got.
Okay. Do we have other questions? Oh,
hello.
Lafika. Yeah. Go ahead, Lafika.
Okay. Well, first, thank you, Dr. Evans, for the wonderful presentation. I just wanted to get something, to understand something. Earlier you mentioned that magnetic monopoles will strictly be found in the unobservable universe. I wanted to know why that is.
Well, we don't see any. So either they don't exist or they exist in part of the universe that we can't see. And this is why Alan Guth came up with the idea of cosmic inflation, because he was basically saying because the universe underwent this brief period of rapid expansion, the observable universe is a tiny part of the actual universe. And it just so happens that in the tiny bit that we can see, there are no magnetic monopoles, but that they really do exist. So that was why he came up with the whole idea in the first place.
So a follow-up to that. So this would mean that probably they don't exist. It's just that we're assuming that they do exist, but it's unobservable.
Well, we don't know is the short answer. If they are in the unobservable universe, the question is, do we have any way of actually detecting them? I would naively say, no, we don't, because they're in a part of the universe that we can't observe, but maybe someone who knows more about magnetic monopoles can correct me there. We don't know whether they exist or not. According to particle physicists in the standard model, they should exist.
Okay. Thank you so much.
Thank you. We have a question from Mapalosi. Is that if the temperature was high at the beginning of the universe, does it mean the entropy was low?
Oh, yes, I guess it does. I think it does, yes. The universe was extremely hot at the beginning, and in fact, going back to what Gamow thought, that all of the elements were created in the early universe, we now know that only hydrogen and helium and a tiny amount of lithium were created in the early universe. And then unfortunately, to go from helium to carbon was not possible in the, I shouldn't say unfortunately, it turns out that to go from helium to carbon in the early universe was not possible because the temperature had dropped too much. So all of the elements beyond hydrogen and helium and a trace amount of lithium are actually created in stars. And what I find kind of interesting about this story is Fred Hoyle was wrong about the correct cosmology. The steady state theory is definitely incorrect, but he was correct about elements mainly being created in stars, and Gamow was wrong about that. So it's kind of a draw in the sense that Gamow was arguing for a hot early universe and a Big Bang model, and Hoyle was arguing for steady state. But then it turns out that Hoyle was correct about where most of the elements are created, which is in stars and supernovae and things like that, and only hydrogen and helium created in the early universe.
Okay, thank you. We have a question from Dr. Schipper, I think.
Yes.
Oh, thank you very much. Thank you, Dr. Evans, for the wonderful talk. Quite illuminating. But you know, I have two questions.
Mm-hmm.
One is concerning the time before the decoupling of photons and matter. I don't know if you can you please elaborate a bit more in terms of the existence of them, or what was existing when before they decoupled, how was the photons, how was and so forth. And the second question is concerning the I didn't quite get the other graph that you showed. It was some multipolar graph, and there was something I didn't quite understand the graph. I don't know if you can possibly tell me what the graph is and say.
Well, I did show several graphs, so I don't quite know which one you are asking about, but I'll take a guess. And if it's not this one, you can correct me. So let me quickly bring this one up. And if it's not the one that you're asking about, then, oh gosh, I got to go through the whole thing now of choosing the correct window again. Okay, so I'm hoping you can.
Yes, is it this one? The multipolar.
Right.
Yes.
Okay, well, that was a good guess on my part. So what this is showing is the essentially, as a function of angular scale, which is the x-axis, it's showing the variations in temperature from the average temperature of the cosmic microwave background. So the highest peak, as you can see, is at an angular scale of about 1 degree, and that has temperature fluctuations which are about 5,500 millionths of a Kelvin from the average temperature, and then the subsequent peaks are obviously lower, but they happen at higher angular scales. So the important thing is that theoreticians fit the data with a model, and the model that fits the data fit the data the best is the parameters that I show over to the left, where you have expansion rate of 72, an age of 13.7, and so on and so on. So you can use this detailed study of the power spectrum of the anisotropies to determine these important properties of the universe.
And then I think the other question was about, oh, sorry, go on. Yeah.
Oh, yeah. Okay, no, thank you very much. I was about to remind him of the first question.
Yeah, well, what was the first question again? Because you cut out when you were talking, and so I didn't catch it. Can you repeat the first question, please?
Oh, so sorry. I just wanted to understand the nature of existence of photons and matter before the decoupling. How were the photons existing and so forth?
Well, so until the decoupling, the universe was a plasma. So the photons were constantly interacting with matter, which is essentially how you produce black body. Black body radiation is produced when you have matter and radiation in thermal equilibrium with each other. And so you know, the universe was a black body expanding and cooling all the time. But until it had cooled enough for the hydrogen, which made up most of the universe, still makes up most of the universe, to become neutral, the photons couldn't get anywhere. They were trapped. And then when the decoupling happened, the photons were able to travel essentially freely, and that is the light that we see as the cosmic microwave background. So it's the oldest light we can see in the universe, because before that the universe was opaque to radiation.
Oh,
okay. Oh, sorry. Yeah. Thank you for that question. And I think we just have time for one more question, actually, because I see the clock is ticking past our time. So, Stuart, I think you have one more question. You're mute at the moment, Stuart. You want to ask that? Yeah.
Okay. All right. Thank you, Dr. Evans, for your talk.
You're welcome.
I just wanted, the reason why I was asking question 2 is, as someone who's working on quantum gravity, I have difficulty in having the B modes. The B modes don't appear when I do my calculations. So I had a feeling that maybe in their absence of the detection of B mode means that quantum gravity could be on some track, because it's difficult for me to get the B modes
that's
from quantum gravity.
Well,
there's only the E modes.
We all know that this is sorry.
And the gravitational wave detectors that are currently, yes, the gravitational wave detectors cannot distinguish whether the waves that are coming are B modes or E modes.
Right. Yeah.
So the inflationary, the CMB, the BICEP experiment, if it fails to detect the B modes, it might mean that the inflationary cosmology might have to do with quantum gravity.
Correct. Yes.
And not the classical.
And I mean, you know, if we believe in the sort of symmetry of the laws of nature, given that the 3 forces of nature of the 4 forces of nature we know about, 3 have a quantum theory and gravity doesn't. I think most people working on fundamental physics would agree that there must be a quantum theory of gravity. It's just a question of finding one that works, whether it's string theory or loop quantum gravity or whatever. As you say, if we fail to detect the B mode polarization, let's say in the next 10, 15 years, as we build more and more sensitive experiments, it means one of 2 things. Either it's not there, or it's there, but we just haven't been able to detect it because it's weaker than predicted. And if it's not there, we obviously need a new theory, because the current theory predicts it should be there.
Okay, thank you very much. That's what I wanted. Maybe I'll send you some of my work on that issue. Yes.
So you'll be hoping that we don't detect it, basically.
I'm not hoping. I'm just saying, if they don't detect, it means quantum gravity is on the right track.
There we go.
Yeah, sure. Thank you very much.
You're welcome.
Okay, I see we have one more question, but I think bearing in mind that we are slightly overdue for a committee meeting, we'll have to, if Lafika, you could email Rhodri with your question to get the answer to that, then I think that would probably be the way to go. Otherwise, sorry, go on.
I'll quickly jump back to my title slide, which has my email address. And if you want a copy of my book, as I say, I'm happy to send it to you for free. I have PDF copies. I'm not wanting anyone to pay for it, even though that probably wouldn't make Springer very happy. So my email address is there on the slide, so you can hopefully see.
Okay, well, thanks again, Rhodri, for a superb talk, and we thank everybody for attending. There are some superb questions as well, actually, at the end there, I have to say. And there'll be another presentation in a month's time, so we'll look forward to seeing everybody there again. And thanks to Dr. Schipper for setting all this up as well, and good night, everybody, and see you soon.
Thank you.
Okay, thank you. Bye.
Oh, thank you.